Hello viewers, welcome back to our series of lectures on chemical bonding. In today's session, we will take up semiconductors. We will basically discuss about the structure, types and conduction mechanisms in case of semiconductors. The session is planned as follows, that is, to begin with, we will briefly review what we did in the previous session, and then thereafter we will talk about conduction in solids in general. Having talked about it, then we will come down to semiconductors per se, and within semiconductors we will talk about the intrinsic semiconductors, and we will take up the mechanism of conduction in case of intrinsic semiconductors. Thereafter we will move on to the extrinsic semiconductors, and herein we will take up two types of extrinsic semiconductors, that is N type semiconductors and P type semiconductors, and towards the end we will try to sum up what we do in today's session. So, that is the outline of today's session. Okay. Now, let us see what we did in the previous session so far. What we basically decided was that in past few sessions we revisited the basic aspects of crystalline solids and then took up the salient features of structure of ionic solids in general. Thereafter, we described the characteristic structures for ionic solids of AX type and then rationalized them in terms of the radius ratio rules and things like that. Thereafter, we discussed different types of defects in such lattices, and then we came down to the metallic bonding, and then we saw that what are different modes of binding which can be explained in the context of metals, and then rationalized the properties of metals in terms of these modes of binding, that is metallic bonding per se. Okay. Now, let us move further and come down to semiconductors, and before that we basically recall a few more things here. Firstly, you remember that all crystalline lattices intrinsically have defects, that is what we established in our previous sessions logically. And then we also know that these defects are important for many properties of solids, because in the absence of these defects the metals or any solids may be not put to use the way they are normally done. Further, these defects can also be introduced, that means some materials are intrinsically defective, that means they have got intrinsic defects in them, but in some cases we can even introduce such defects and they are called as extrinsic defects, and this is what is of interest to us in today's session. That is, when we talk about semiconductors, essentially we are dealing with extrinsic materials, which is a very important domain of semiconductors. Then one more thing we did earlier was, that is, the electronic structure of metals can be explained in terms of band theory. We discussed that in detail in the previous session. That is something which we have done so far. Now, let us continue from here and then see that if we talk about conduction in solids in general, and we will pick up threads from the previous session where we talked about conduction in metals. Let us see that you remember that in case of solids, metals per se, there are two possibilities, there are two mechanisms by which conduction can take place. One, the typical case is for lithium we discussed in the previous session, wherein what happens is that we got different bands there. There is a 1s band which is completely filled, that is the inner band over there, and then there is a 2s band here. You remember that these bands are obtained by kind of combination of atomic orbitals of a large number of atoms there. Okay. Now, in case of systems like lithium, what happens is that this 2s band here, half of it is completely filled and half happens to be empty, and then this filled band is called as a valence band and the empty band is called as a conduction band here. And there is no difference in terms of energy between this valence band and the conduction band, and with a little amount of energy the electrons can move from the valence band to conduction band and start conducting. That is one way in which the conduction takes place in case of metals as per the band theory. The second aspect we saw was in the context of things like beryllium. In case of beryllium, we saw that when we talk about the band structure of beryllium, we find that 1s band is perfectly fine, similar to what we had in case of lithium here. Similarly, same is true of 2s also. But when it comes down to 2p band, we find that this 2p band, the bandwidth of this band is quite larger than the difference in the energies of this 2s and 2p orbitals. And thereby what happens is that this 2s and 2p overlap. That means that this 2s band and 2p band overlap, and as a consequence what happens is this energy levels of this 2s band remain empty and some of the 2p orbitals are filled up there, 2p band are filled up over there. And then what happens is that when we give energy to a system, the electrons in these energy levels over there, or these molecular orbitals here in the valence band, they go to the conduction band and start conducting. That means there are two possibilities. One, similarly, typically we go from the valence band to conduction band straight away, but in the second possibility is that we got overlapping between the two bands, and then because of overlapping, this the difference between the conduction band and valence band becomes very small there, and then conduction comes into play. Okay. Then going further, when we talk about elements of third period, that is where we stopped in the previous session. When we talk about elements of third period, the metallic part of it, say sodium, magnesium and aluminum, when we look at the band structure here, what we see is there is a typically 1s, 2s, 2p bands, and all of them, they are common to each one of them. But when you come to the 3p and 3s, we find that since the 3s orbital is singly occupied, in all it is 3s1, it is 3s2, this is 3s2, 3p1. Now, when these orbitals kind of combine together to give us the bands, we find that the 3s band and 3p band are overlapping to a very great extent, to such an extent that we can represent them as a combined band. We are representing it as a 3s plus 3p band over there. Okay. So, that is the three representations here, one for sodium, magnesium and aluminum, and each one of them we are showing them as a combined band there. Now, if you look further, in case of sodium, what do we have? We got one 3s orbital, and then there are three 3p orbitals there. So, total of 4 orbitals per atom, and there are n atoms there. So, n atoms, 4 orbitals each, that will give me 4n atomic orbitals will combine to give me 4n molecular orbitals. And since there are 4n molecular orbitals, the capacity to hold electrons will be 8n, because each orbital can take up 2 electrons there. And what do we have? In case of sodium, we have got only 1 electron, that is in the 3s orbital there, and n atoms there means there are n electrons. So, the capacity of this band is 8n, and only 1n electrons are to be occupied. So, what happens is only 1/8 of these orbitals here in this band, they are occupied, and rest remain empty over here. And then when we give energy, the electron can go from these occupied energy levels to the empty energy levels over there, and the conduction starts there. In case of magnesium, the occupancy is about 2/8, that means 1/4 of it. In this case, it is about 3/8, otherwise the 3 remain the same. So, that is the way conduction takes place in case of the metals of the third period, that is sodium, magnesium and aluminum. Let us move further and see what happens in case of the other elements of the third period, that is carbon, silicon and germanium. Let us look at the band structure here. That is very interesting. What you find is that in case of carbon, carbon again has p electrons over there, and when we talk about a band structure, we are not giving the core electrons over there, that is the 1s, 2s and things like that. That inner orbitals we are not showing here. So, what we see is, if I look at the outermost valence band here and the conduction band, we find that in case of carbon, there is a enormous difference in energy there, to the extent of about 530 kilojoules, which is a large amount of energy. And as a consequence, what happens is that the electrons in the valence band, they are not able to go to the conduction band, and carbon does not conduct, it happens to be an insulator there. Okay. When we move from carbon to silicon, we find that we have got similar band structure, but the band gap becomes lesser here. It is about 106 kilojoules per mole, and this band gap is reasonably big, but not so big that electrons cannot move from here to there. In this case, even in case of germanium, the band gap is even smaller, about 64 kilojoules per mole. Now, what happens is, in these two cases of silicon and germanium, what you find is that some amount of energy given to a system, the electrons can go from valence band to the conduction band, and they can conduct electricity to some extent. Since they cannot conduct electricity like metals, so they are called as semiconductors, whereas carbon happens to be an insulator, as it cannot conduct electricity. The reason being that this band gap is very large. The numbers I have given here in terms of the band gaps here, they actually are the values at absolute 0. At room temperatures, it will be slightly different over there. Okay. Now, so what we see is that when we talk about the elements of third period, we find that sodium, magnesium, aluminum, they are metals, because in all the 3 cases, we hardly need any energy for the electrons to go from the valence band to conduction band and start conducting. On the other hand, when you come down to carbon, silicon and germanium, we find that carbon is an insulator, silicon and germanium are semiconductors there. And this is the class of materials which we are interested in today's session there, that is the elements or the materials which are semiconducting in nature, that is they have got a very small band gap. Let us try to define what semiconductors are. Semiconductors basically are the solids having a small band gap, that is the energy difference between the valence and conduction band happens to be very small there. Okay. Further, if you look at the types of semiconductors, there are two types here. The first one is called as intrinsic semiconductor. Intrinsic semiconductor is the one, as the name suggests, intrinsic, something which conducts by itself. Okay. So, the materials which conduct by themselves are called as intrinsic semiconductors. We will talk in details about this in a short while from now. The second variety happens to be extrinsic semiconductors. These are the materials which are made to conduct by introducing some kind of a impurity or things like that from outside. Extrinsic factors are involved in this case. Now, let us talk about intrinsic semiconductors first. Now, if we look at intrinsic semiconductors, the materials like say silicon, what happens is if I look at the structure of this at absolute 0, we find that all electrons are in the valence band and the conduction band happens to be empty. So, at absolute 0, given silicon happens to be an insulator, because all electrons absolute 0, we know that it is ideal situation, it does not happen. But when in terms of argument, we find that a silicon at absolute 0, all the electrons will be in the valence band and the conduction band will be empty there. Okay. So, it will be behaving like an insulator. But if I raise the temperature, bring a material to say room temperature. Now, when we come down to room temperature or any temperature higher than absolute 0, we find that what happens is that some of the electrons from the valence shell or valence electrons, they move on to the conduction band there. When they move to conduction band, we can see it here, that is the electron, this electron has come over here, there is another electron somewhere here. So, these are the electrons which are moved from their place in the valence band, they come down to conduction band and that is where they start conducting, and this material becomes conducting at room temperature. And since the conduction is not as large as that of metals, it is conducting, but to a very feeble extent, so that they are called as semiconductors there. So, a material like silicon will be semiconducting at room temperature. Let us move further. Now, what you see is, so they are the free electrons over here which are going to be responsible for conducting or making it a conductor there. And since electrons are moved from some places, so we will generate what are called as holes there. If the places where the electrons were expected to be there in the valence shell there, but it becomes a hole over in the valence shell there. Now, such mechanism of conduction wherein the electrons move from the valence band to conduction band and start conducting, this is called as intrinsic semiconduction. Please bear in mind that whenever we talk about semiconductors or semiconduction, essentially we imply that the conduction is there, but not as significant as in case of metals there. Okay. Now, silicon and germanium happen to be the most important commercial examples for semiconductors there. Let us look at the structure of these. The crystal structure are like diamond, and we know that in case of diamond, a carbon atom is tetrahedrally bonded to 4 carbon atoms over there. Same is true in case of silicon also. And we find is that that is the kind of structure we have, that is called as typically called as a diamond structure, and here what we are talking about is the structure of silicon here. So, these are silicon atom, one silicon atom is attached to 4 silicon atoms there. So, each one of them will be attached to 4 neighbors as silicon over there. So, that is very large giant structure we have in case of diamond or in case of even silicon also. And typically such structures are difficult to represent. So, what do is we take recourse to a 2-dimensional representation here, wherein we show these atoms here. So, all these are silicon atoms over here. If you look at any one of them, so this is bonded to 4 neighbors here, 1, 2, 3, 4 and so on and so forth. And we can see that this bond is shown in terms of a electron pair over there. So, the 4 electron pairs surrounding a silicon atom, that indicates that it is bonding to 4 silicon atoms in the neighborhood with it. Okay. So, that is how we represent a silicon element over there. Okay. Now, if you look at in terms of the conductivity, which I have been telling number of times here. So, typically in case of germanium and silicon, we find the band gaps of the order of 68 to 106 kilojoules over there, and the conductivity essentially depends on the number of electrons in the conduction band. and that actually will depend on two things. One, what is the band gap over there? Say at a given temperature, say room temperature, germanium will have more conduction as compared to silicon because the band gap is lesser there. And secondly, suppose I talk about silicon at a given temperature, it has got certain conductivity, and if I raise the temperature, what will happen? More electrons will go from the valence band to the conduction band, and the conductivity will increase. So, that is, the conductivity of semiconductor depends on the temperature and also on the band gap. Lower the band gap, higher the conductivity, higher the temperature, higher the conduction there. That is one bit of it. And another thing which you have to just relatively place things over there. So, what you find is the metals are highly conducting there. So, the numbers are fairly large, okay. And insulators have got very small conduction over there, almost negligible or very insignificant kind of conduction there, and semiconductors are in between the two. That is why it is called as semi. That means, the conductivity of semiconductors is in between that of the insulators and the metals over here. Okay. Let us move further and see that the intrinsic semiconductor, as I just mentioned, the conductivity increases with temperature because more electrons will be able to move from the valence band to the conduction band there. And you see that this behavior of semiconductors is opposite to that of the metals. In case of metals, if we raise the temperature, the conductivity decreases there. That is very interesting observation we have to keep in mind. Okay. Let us move further and talk about the mechanism of conduction in case of intrinsic semiconductors there. That is very important. Please pay attention to what you are saying. So, what do we see is, this is some representation of silicon as a semiconductor there. So, what you see is that each silicon atom is bonded to 4 neighbors there, and then this pairs of electrons are indicative of the bond formation there. Further, what we can observe here is that this is an extra electron here, so is this one. These are the electrons which are moved from their original valence band, come down to the conduction band there. So, they are the ones which are going to be responsible for conduction of, in case of this silicon metal there, silicon element over there. In addition to this, what do we have is, we have got some holes there. So, this is one hole, this is another one. So, there holes are the places from where the electron has moved. That means, initially at absolute 0, all the electrons were around the silicon atoms there. That means, all this was here at absolute 0, but at room temperature, this electron has moved from this place and come down to say somewhere here. So, this has become a hole, and this has become a free electron in the conduction band, which can conduct and make it semiconducting there. Okay. Now, how does it conduct? Let us see that. Basically, what happens is, say we have got a hole here. Let us try to focus attention onto some of these electrons and holes over here. What happens is, when we apply the potential, some electrons, say this electron here, which is here, that moves to this hole over there. That means, an electron which is a valence electron, that moves to a hole over here, and we generate a new hole there. Then what can happen is, another electron can move and come down to occupy this hole, and the hole is created here, and this process continues. So, what you see is that an electron is moving from one place to another and occupying a hole, and then that process continues, and the effective outcome of this whole series of kind of movement we have shown here essentially is, effectively speaking, an electron which was here has moved somewhere here, and a hole which was here initially now has reached over here. Effectively speaking, there are two kinds of movements here. One, movement of electron, that is in this direction. That means, electron has moved from this direction, from here to here in this particular direction, and the hole has moved in the direction opposite to it. So, the conduction is in terms of the electrons and effectively movement of electrons over there. So, that is how conduction takes place in intrinsic semiconductors like silicon there. Okay. Let us move further and talk about the second kind of semiconductors, that is called as extrinsic semiconductors. What we see is that in case of certain materials, say silicon and germanium, we know that they have got intrinsic conduction there, but suppose we need this material which is more conducting than the intrinsic conductivity of say silicon or germanium. So, what do? We can add some kind of impurities from outside and make them conducting more than what they are intrinsically over there. So, this kind of mechanism the process is called as doping. That means, you take a sample of silicon, it has got some conductivity, but we dope it with some material from outside such that the conductivity increases. This process is called as doping, and the impurity which we introduce into the silicon sample is referred to as dopant there. Now, depending on what kind of impurity we introduce, there are two types of semiconductors we can create, two types of extrinsic semiconductors. One is called as N-type semiconductor, another one is called as a P-type semiconductor. The type will depend on what is the nature of the dopant I am introducing. We will talk in detail as we just proceed from here. Okay. Let us start with what are N-type semiconductors there. N-type semiconductors are the ones which are obtained by introducing an impurity of, say, phosphorus or arsenic into a sample of silicon there. That means, you take a pure sample of silicon and introduce an impurity of phosphorus or arsenic, and we have to think of an impurity which has got about 5 valence electrons there, because silicon has got 4 valence electron. That is very important. That means, I am introducing an impurity which has got 1 valence electron extra, or rather more than that of silicon there. Okay. So, what happens is, so when we do introduce this kind of a dopant into silicon, what happens that some of the silicon atoms are replaced by the impurity atoms there. So, it is shown here that they all are silicon atoms there. One of the silicon atom has been replaced by a phosphorus atom, that is an atom of the impurity there. It could be phosphorus or arsenic or whatever. Now, what happens is, the 4 of the valence electrons of the impurity form 4 bonds with the silicon atoms. So, because this phosphorus has got 5 electrons there. So, it will form 4 bonds there, 1, 2, 3, 4. It forms 4 bonds with the 4 neighboring silicon atoms there. And what happens is, the 5th electron here, this one here, this one remains free onto the phosphorus atom there. And then, if I am talking about this material at absolute 0, so this valence this electron, the extra electron will stay onto the phosphorus atom. But if we increase temperature, this electron can move and then cause what is called as the conduction there. So, that means, this electron which is at phosphorus to begin with, but when I bring it to a room temperature or higher temperature than absolute 0, so this electron can move from the valence shell or valence band to the conduction band and start conducting, and this mechanism of conduction is referred to as extrinsic conduction there. And this typically the extrinsic conduction is more than the intrinsic conduction, because intrinsic conduction is very small, but extrinsic conduction could be much more than that, and that actually will depend on what is the magnitude, what is the extent of impurity we introduce into silicon. If we introduce very small amount of impurity, there will be lesser conduction there. Add more of it, conduction will increase, because there will be more electrons which will be available to move from the valence band to the conduction band and start conducting over there. Now, since in such cases the current is carried by excess electrons, because that is excess electrons which are provided by the dopant atom there, this is called as N-type semiconduction. Now, let us look at N-type semiconductors in terms of the band structure. So, what you see here is that this is a typical standard band structure here, and this is the valence band of silicon atom, and this is the conduction band for silicon there. And we see that this is the initial band gap, which is fairly large. That is why this silicon happens to be semiconducting. It is about 106 kilojoules per mole. But when I introduce the impurity into this, impurity of phosphorus, and we find that the band of phosphorus happens to be somewhere here. The energy level for phosphorus atom happens to be very close to the conduction band there. And since this band is occupied in case of phosphorus, because that extra electron we talked about, it is in this particular energy level here. And since now the electron is in this particular band over there, that is a phosphorus band, when I give little energy to that, the electron can go from this dopant level to the conduction band and start conducting there. And essentially what happens is, by introducing this impurity, the effective band gap has become so small here. That is how the conduction is increased. That is how do we explain the extrinsic conduction there. That is, by introducing the impurity, we have been able to reduce the band gap between the valence band and the conduction band of the initial material, that is silicon in this case. Okay. Let us move further and talk about the second type of semiconductors, second type of extrinsic semiconductors, they are termed as p-type semiconductors. In case of p-type semiconductors, what do we do? It is similar to what we had in case of n-type semiconductors, that is, we take a pure sample of silicon and add an impurity, but in this case what do we do is we add an impurity of say boron or indium. That is, the important thing is that these two elements here are the ones which have got only 3 valence electrons, that is 1 valence electron short of that of silicon there. Silicon had 4, so we are introducing an impurity which has got 1 electron less in the valence shell there. Okay. So, what happens? Similar to what we had in the previous case, here again some of the silicon atoms will be replaced by the boron atoms over there. So, suppose I am reducing impurity of boron into silicon there. Okay. So, then this boron has got only 3 valence electrons. So, the 3 valence electrons of boron will form 3 bonds with the neighboring silicon atoms there, and what will happen is the 4th neighboring silicon atom is not bonded there, because boron has got only 3 valence electron, it can bind only to 3 neighboring silicons, it cannot bind to the 4th one there, which implies that there will be a vacancy, there will be a positive hole be created at the boron atom over there, because it is not able to bind to silicon has got an electron, but boron does not have that electron to bind to silicon atom there. Silicon atom is there, and this, if I look at this material at absolute 0, this positive hole will be located at the boron atom itself. But when we bring it to room temperature, and this hole can actually move, and at normal temperatures this valence electron on the adjacent silicon atom moves into the hole there. That is, there is a movement of an electron from silicon to this void here or the hole here over here, and we create a new hole over here. And this process can continue, another electron can come from here to here, the hole will move somewhere here, electron will come here. In this case, that is, a new hole will be created at a silicon atom there, the neighboring silicon atom from where the electron has moved to this hole located at the boron atom there. And this hole hopping mechanism continues, as we showed in the case of silicon conduction there, and this is what leads to electron movement in the opposite direction. I mean, hole hopping will be in one direction, electron movement will be in the direction opposite to that. That was what we demonstrated earlier too. And as a consequence, this conduction is also called as extrinsic conduction, because the conduction has come into play because we are introduced an impurity which has got 1 electron short there. That is, we have been able to create a hole there, and the electron movement from silicon to this hole and the process continuing leads to the conduction in the material there. So, such conductors are called as extrinsic conduction, and since in this case the current is carried by hopping positive holes, this is called as a p-type semiconduction. The mechanism is that is, this process is called as p-type semiconduction there. Now, let us again look at p-type semiconductors also in terms of the band structure. So, what do we find? It is a similar picture what we showed earlier. So, what we see is that this is the valence band of silicon atom there, this is the conduction band of silicon there. But when we introduce an impurity here, that is the dopant level is somewhere here, which is close to the valence band. Effectively, now what can happen is, because there is a hole here, because this dopant level is short of an electron there. Now, what will happen is, with a little amount of energy, the electron will move from this valence band of that is the silicon atom there, and come down to the hole which is located in the dopant level over there, and it will start conducting there. We will be creating a hole here, and the process will continue thereafter. What it amounts to doing is, that is, effective band gap now has become just this much. In the absence of the dopant level or the dopant over there, pure silicon, the band gap was so large there. But because by introducing this impurity, we have been able to reduce this effective band gap, and then thereby the conduction is there, and this is called as p-type semiconduction there. Okay. Now, let us sum up what we have done today. What we have done today is, basically we started by reviewing the contents of the previous sessions. Thereafter, we came down to discussing the conduction in solids in general, wherein we recalled what is called as the band theory, which we discussed in the previous session, and we talked about conduction in case of metals and non-metals of the third period there. Thereafter, in this process, we came down to defining what are semiconductors and talked about its types possible there. Having done that, we move further and explained the conduction mechanism in case of intrinsic semiconductors like silicon, how does it conduct, Then thereafter, we talked about the formation and conduction mechanisms in case of extrinsic semiconductors over there. In the next session, we will talk about lattice energy and its, because basically we are talking about ionic solids, and in case of ionic solids, lattice energy is a very important parameter. We will see that what is lattice energy, how do we determine that. We will talk about the theoretical approach and also experimental determination of lattice energy in the next session. Thank you.